Okay, so let's start with the arc length and the area of a sector for a circle. So we're looking at the arc length, and this is all in radians that we're going to be referring to. Okay. So this is basically a summary of the stuff that happened in year 10. Okay, so it is technically presumed knowledge, but again, we will go over it just to make sure that we understand. So let's say that we have a circle. Some form of circle. That's not a circle, that's an ellipse. We don't want an ellipse, we want a circle. Circle. Okay, so apparently my pen is not wanting to draw it for me. There we go. So a circle, and let's say our circle, okay, has a radii, and another one like that, from the center, and we'll call it O, that's the two radiuses there, and it's some angle in the middle, and between the 2 points where the radiuses touch the edges, we have a length around the outside, which we call the arc length. Now that arc length is just as it is, okay, there's nothing too tricky about that, but what we can do is we can actually work out or calculate what the how to work out the angle of a we can work out what the length of the arc length is. Now, we're going to be using the definition of angle size in radians. So that is that theta is equal to the length on the radius, so the arc length on the radius, okay? And so that just means that the length of the arc is equal to the radius times the angle, which makes sense if you think about it, because whatever the angle is, we're just going to multiply it by what the radius is, and that will give you, it's essentially a fraction of your circumference, okay? So in this case, a full circle is 2 pi, as we know. So that would be 2 times the radius, okay? But essentially the arc length is exactly the same, except it's just our theta is our angle. Now, we were also going to talk about the area of that sector. So let's say we have the same sector again. Now, it's a little bit different for the sector. So the area, okay? The area of the sector is theta on 2 pi, okay, because it's essentially saying, okay, what fraction of the full circle, so our full circle is 360 degrees, so 2 pi in radians, times the area of the circle, okay? But we know, if I put these in, area of circle is pi r squared, okay? So taking out some factors, we've got the pi's that are common. So what this is going to leave us with is that the area of the sector is equal to the angle, or half the angle, r squared. Okay? And that's pretty much it. So let's have a look at this in an example. What is the perimeter of a sector subtending an angle of 120 degrees at the center of a circle with a radius of 20 meters. So what we're thinking of is we're thinking of a sector like this. It's not the full circle, and we want to find the perimeter, so it's the total outside. Now it's 120 degrees on the inside here, and we know that the radius is 20 meters, so it's 20 meters here and 20 meters there. The total perimeter, okay, well, we need to work out what the arc length is, so it's going to be L plus 20 plus 20. So the arc length is what we need to find first. So using the formula from before, the arc length is equal to r times the theta. So it is equal to, and this is in radians. You need to make sure it's in radians. So r is 20 times 120 degrees of that. So 20 times 120. So 20 times 120 degrees, and that should give us too big. Of course, we need to change the 120 degrees into radians. Why didn't I think of that? So, change to radians. So if we think back to our angles, 120 degrees is the same as 9 degrees plus 30. So, a right angle, and then it's 30 degrees in that direction there. So it's the same as pi minus So it's the same as pi minus 60 degrees. So 60 degrees is pi on 3. So 120 degrees. So 120 degrees. Oh, well, let's just do it the easy way. Why am I worrying about all this? Converting 120 degrees to radians. So 120 times pi on 180 is equal to, so zeros cancel, 12 divided by 8 is 2 on 3. So it's 2 pi on 3. So it's 20 times 2 pi on 3. A lot harder than I'm making it. So 4 pi on 3 is our length, arc length. Now, because we want the perimeter, so perimeter is equal to 40 pi on 3 plus 20 plus 20, which is equal to 40 pi on 3 plus 40. Or if we're going to put it all on the top of the fraction, it's 40 pi plus 120 all over 3 like that. And so that's our perimeter. Now, part B said, what is the area of the sector with the same dimensions? So part B is a sector now. So the area of a sector, so a half the angle, and remember the angle is in radians, so radians, half the angle times, is it r squared? Half the angle times r squared. Yep. So in this case, it's going to be half times our angle that we worked out, which is 2 pi and 3, times the radius squared. Now the radius squared is 20 squared. Okay, we'll work that out in a moment. So half times 2 pi on 3 is 2 pi on 6, or pi on 3, if you will. So we can write that just as pi on 3. 20 squared is 400. And so that means, well, our perimeter in our area is going to be similar. Not similar, really. So it's 400 pi on 3. And there we go. And that's in meters squared. And this one is meters. So there we go. There is our arc length and there is our area. So we remember keeping them in exact form because it's just much easier to deal with if we need it later on. And yeah, nothing different about that. So the arc length, just remembering to change, make sure we change our conversions to radians. So I'll see you guys in the next one when we're going to talk about the extra stuff that we need to do for this bit.